G'day, I'm James, and welcome to the beauty and the thinking behind matrices and their arithmetic. So to motivate this subject, let's begin with this puzzle. What I've got on the board here is a diagram. They're the route maps of two particular airlines going between three cities. I've just labeled the cities City 1, City 2, and City 3. And one airline company I'm showing in red, I'm calling them Air Riders, has all their route paths between the three cities shown in red. And the other airline company, Jet Blasters, I'm showing in blue, and I'm showing all their route paths between the three cities. For example, to go from City 1 to City 2, Air Riders, the red one, has two possible routes you can go from City 1 to City 2. And Jet Blasters in blue only has one route that goes from City 1 to City 2. Air Riders has a joyride. You can actually go from City 2 up into the air and come back down again. Whoops, sorry, this other way. They have one joyride from City 2. Whereas Jet Blasters has two particular joyrides from City 1. So you see what this diagram is doing is all the possible route paths you can go between the three cities, between the two different airline companies. So here's my puzzle. I want to count a very complicated journey. For some reason, I want to do a 6-leg journey. I want to ride the red line, the red line, the red line, and then the blue line, the blue line, the blue line. I don't know why I want to do that, but I want to do that. But I want to count all the possible ways I can start from City 1 and end up back at City 1 by riding 3 red lines, Air Riders, followed by 3 blue lines. Whoops, 3 blue lines, Jet Blasters. For example, one way could be red, 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 blue, do that joyride again, blue, and do the other joyride, blue, back from City 1. Got that? Another path could be, I could do red, 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 blue, 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 back at City 1. So, looking at this diagram, how many different ways are there to ride from City 1 back to City 1 by doing 3 red paths followed by 3 blue paths? My real question is actually, how could you work that out? How could you work out all the different ways you could do that in the most efficient way? And I just chose City 1 to City 1. Then I wonder how many ways are there to go from City 1 to City 2? 3 reds, 3 blues. Or City 3 to City 1, 3 reds, 3 blues. It'd be a lot of counting. So there's got to be a clever way to count these things. And that is the puzzle for today, and that is where the theory of matrices is going to come in and help us out. All right, so I'll leave that puzzle hanging, but let's now get going with the theory. Okay, so let's use this example of airline routes to actually motivate matrices. Now this diagram we have here of all the routes for Air Riders in red and all the routes for Jet Blasters in blue is actually visually very complicated. It's hard to take it in. So it makes sense to actually try to encapsulate this information in a more systematic way, namely with a table. For example, I've just focused on the Air Riders in red, and I've made a table here of all the cities you can come from. You can come from City 1, City 2, or City 3, and all the cities you can go to, City 1, City 2, or City 3. And what I've got in this table is all the routes that go between the various pairs of cities. For example, to go from City 1 to City 1, there are no routes in red that go from City 1 to 1. Air Riders offers no joyrides. But to go from City 1 to City 2, there's actually 2 different routes you can go from City 1 to City 2. 2 different routes. City 1 to City 3, I can see from this diagram there's only one route from City 1 to City 3. One route. And for example, this 2 here means there must be 2 routes from City 2 to City 3. From 2 to 3, is it indeed 2 routes? Yes, there are 2 routes. So what I did there is just encapsulate all the information in the diagram for the red routes in a table. And I can do the same thing for Jet Blasters in blue. In fact, I'll do it right here. How many routes are there from City 1 to City 1? I see 2 of them. From City 1 to City 2, I just see 1 route from City 1 to City 2. From City 1 to City 3, I see those 2 routes. 2 of them. City 2 to City 1, City 2 to City 1, there's 1. City 2 to back to itself, none. City 2 to City 3, none. City 3 to City 1, there's only 1 route. City 3 to City 2, there's nothing. And City 3 to City 3, there are no joyrides, nothing. So there's a table that represents all the information about the blue paths. The tables are much easier to take in. In fact, tables come up a lot in mathematics and people give names to tables. Any rectangular array of numbers like this in a table is called a matrix, M-A-T-R-I-X, and the plural of matrix is matrices. So now, that's it. A matrix is just a rectangular array of numbers, like a table. Except we don't actually need the from and the to and the city numbers, because we understand where this came from. We don't need the from and the to, so actually maybe get rid of that and just have literally the rectangular array of numbers. That's called a matrix. And people tend to put them in great big brackets or parentheses. They either use round parentheses like this. Sometimes they might use square parentheses, depends what book you're using, what text you're reading. But I think most people will go with round, so I'll go with round. There's one matrix. I'll call it matrix A for the air riders group. And here's a matrix B for the jet blasters group. And I'll use the round parentheses there, the round brackets. Just for a piece of notation, people tend to give matrices names with capital letters. I don't know why, but it's just become the convention to use capital letters when naming matrices. So here's the A matrix for all the air routes for air riders. Here's the B matrix for all the air routes of jet blasters. And it's understood how to read this from one city to one other city, the number of routes between those two cities. Sorry, a little tongue-tied there. All right, great. Actually, while I'm at it, I might as well just give notation. Now we've got to know what a matrix is. It's just a rectangular array of numbers. I have a square array here. It's 3 rows and 3 columns. So people say this is a 3 by 3 matrix. 3 rows, 3 columns. This one's also a 3 by 3 matrix. Here's another matrix. I'll call it, W. Capital letters, of course. 2, 1, 5, 7, 0, 1, 6, 4. Not quite sure what those numbers are representing for us, but it is a rectangular array of numbers, so it's a matrix. In fact, it's got 2 rows and 4 columns. So this is a 2 by 4 matrix. Great. So when people talk about an M by N matrix, they just mean a rectangular array of numbers with M rows and N columns. That's it. Another little piece of notation doesn't come up that often in the curriculum, but you might see it. I'll just add it here. For example, this 2 here, it's in row 2, column 3. So I'd say, in the matrix A, the row 2, column 3 entry, subscript 2, 3, is a 2. Or if I look at this 0 here, that's in row 1, column 1, and it's a 0. And this one here is in row 3, column 3, and column 3, and it's a 1. So people use this double subscript notation to say, I want the particular entry in a certain row, certain column. So you might see that sometimes, or you might not. It's not too hard to figure out what it means when you do come across it in your life. All right, so that's it. So we've just created 2 matrices that make sense for this airline problem. So let's now play with them. Okay, so I just wrote my 2 matrices for the 2 airlines up higher, because I'll keep coming back to these. But let's imagine now that these airline companies now do different things. For example, suppose airline company A, air riders in red, just doubles the number of routes it has between its various cities. Right now it has 2 routes between city 1 and city 2. Suppose it doubles it to 4. Right now it has 1 joyride from city 2 back to itself. Suppose it doubles it, it makes it 2 joyrides. What matrix would we get? Well, it'd actually be this matrix, but instead of having 2 routes from city 1 to city 2, it'll now have 4 routes. So having 1 joyride from city 2 to city 2, there's the 1 joyride, city 2 to city 2, you'll now have 2 of them. In fact, you can see the count of all the routes now doubles. So now we get a new matrix for that new, bigger airline with all the routes doubled. And it seems very natural to give this basically the same name, A, but let's call it twice A. 2A is just doubling all the entries of A. Does that make sense? So people call this scalar multiplication. We actually multiply the matrix by something, but we just multiply it by a simple number. People call that a scalar sometimes. This is called scalar multiplication. And it turns out 2A to us means just double all the entries of the matrix A. For example, if I had 10B, what does that mean? Well, give me a matrix with all the entries 10 times as big. Great. 10, 10, 0, 0, 0, 0. And what does it mean in our example? It means the jet blasters company has just increased the number of routes between cities tenfold, given 10 times as many options between the various routes it already had. All right, great. So we've just learnt scalar multiplication. Actually, imagine there's a third airline company. I'll call it Cheapo Airlines. Cheapo Airlines. It went bankrupt. It currently has no routes between any cities. There are no routes. It offers nothing. So what does its matrix look like? So I'll call it cheapo and I'll use that as C. If it offers no routes between city 1 to city 1, and no routes between cities 1 and 2, and no routes between 1 and 3, and 2 and 1, and 2 and 2, and 2 and 3, and 3 and 1, and 3 and 2, and 3 and 3, that's what its matrix looks like. This matrix here is called the zero matrix. It's called the zero matrix. In fact, sometimes people represent it with a capital O, which is hard to read because a capital O looks like a zero, but there's the zero matrix, all its entries are zero. And in fact, suppose airline A went bankrupt and all its entries went down to zero. It's like doing scalar multiplication with zero. 0 times the matrix A multiplies all the entries by 0 and the airline's gone bankrupt. All right, so there's a little basic. We've done our first piece of arithmetic with matrices. Feel free to multiply them by the number, and that just means all the entries are scaled up by that number. And it makes good sense in this airline examples when airlines start doubling the counts of routes they offer and so forth. All right, but let's do more arithmetic. All right, suppose now that these two different airline companies, Air Riders and Jet Blasters, separate companies right now, actually unite and become one company. So that actually, now we'll say the red and blue colors don't matter because it's just one company, and the color they go with is, say, purple. So imagine everything here is now purple, red and blue combined. Okay, so this is now the diagram of just one company. What matrix do I get from that one company? Well, for example, to go from city 1 to city 2, there used to be 2 red routes and 1 blue route, which are now combined to make 2 plus 1, 3 routes between city 1 and city 2. To go from city 3 to city 1, it used to be 1 red route and 1 blue route, but now as a combined company it offers 1 plus 1, 2 routes between city 3 and city 1. In fact, it's just the count of routes are added together. So it's like I said, this matrix A, this matrix A, which is 0, 2, 1, 2, 1, 2, 1, 1, 1, got added into this matrix B, 2, 1, 2, 1, 0, 0, 1, 0, 0. I'm not quite sure what my language should be, but I'm doing literally what I did before. Add the individual entries. There used to be 2 routes and 1 route between 1 and 2. 2 routes and 1 route is now going to become 2 plus 1 is 3 routes. Used to be 0 routes and 2 routes is now going to become 2 routes. The 0 red routes from 1 to 1 plus the 2 blue routes from city 1 to city 1, now it's 0 plus 2. 1 plus 2 is 3, 2 plus 1 is 2, 3, sorry, I'm just adding the matching entries. You see what I'm doing? Adding the matching entries. The third row, first column, 2. First row, second column, 1. Third row, third column, 1. And as a check, let's look at this. Let's look at this one. Row 3, column 1, city 3 to city 1, so 3 to 1, there's now 2 routes from 3 to 1, and yes they are. If I don't care about color, there's the 2 routes. There are the 2 routes. All right, so it's adding the routes together has given us what we call addition of matrices, and it seems natural to say, well, to give this matrix a name, namely it's the matrix A, there it is, and the matrix B, there it is, added together. So people call this matrix addition. To add together 2 matrices, just add the matching entries in the 2 matrices. Which then brings a little point home. We lucked out that, yes, row 2, column 1, and there was a row 2, column 1 there. Row 3, column 3, and there was a row 3, column 3 there. The matrices have to be the same size for this to work. If there's a mismatch in size, we're in trouble. For example, suppose I try to add this matrix, 2, 1, 2, 7, 4, 6, and this matrix, which has 4 rows, 5, 1, 7, 8, 0, 4, 6, 2, and only 2 columns. So this is a 2 by 3 matrix and a 4 by 2 matrix, and if I try to add them together, add up the matching entries, all right, first row, first column, great, 7. First row, second column, great, 2. First row, third column, I'm in trouble. Or try this one, 3rd row, first column, there is no 3rd row. 4th row, second column, there is no 4th row. 2nd row, 3rd column, second row, there is no 3rd column. So if the matrices are not the same size, you have no hope of adding them. So you can't. But we can certainly add matrices of the same size, and in this particular interpretation it means like 2 different airline companies just combine their routes together, so we're just adding up all the routes that they possibly offer between different pairs of cities. Kind of makes some sense. All right, so let me give you a practice problem to try, because I've done a lot of talking. Your turn to try something. Back in a moment, I'll clean the board. Okay, so here's my practice problem for you. I've got 2 by 2 matrices, 2 rows, 2 columns, P given by that rectangular array of numbers, and Q given by that rectangular array of numbers. Could you write down for me what the matrix 3P minus 2Q would be? That is, can you figure what 3p means, some scalar multiplication, and negative 2q scalar multiplication, and then add them together? Can you figure what that means? In which case, the result would be another 2 by 2 matrix. Can you write it down? And then when you've done that, try this one. What do you think 1/3 of p plus q means as a matrix? Can you write down that answer as well? Give it a try. Okay, so let's now start attending to the opening puzzler idea. There's namely doing multiple journeys, multiple legs, going from, red, 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 blue, blue, blue. But let me keep it simpler right now. Suppose I want to do a journey, say, going from city 2 to city 1, but I want to do it in 2 legs. I first want to ride the red airline, jet air riders, for 1 leg, followed by the jet blasters, the blue airline, for a 2nd leg. So here's my puzzle. I want to go from city 2 to city 1, first flying a red route, which means I have to fly to some middle city, and then fly a blue route and end up at city 1. How many ways can I do that? All right, well, obviously there are 3 choices of which city could be in the middle. I could fly from 2 to 1 and then 1, or 2 to 2 and then 1, or 2 to 3 and then 1. So I have to check all 3 possibilities and count up all the options within each of those possibilities. And I'm actually going to do that. In fact, the possibilities are fly to city 1, or fly to city 2, or fly to city 3. So let me just write out the numbers again, 1 and 1. So I can either go red, red, blue, blue. All right, so I've got here my red matrix of all the counts of routes, my blue matrix, all the counts of routes for the various different airlines, and all I have to do is go ahead and count them. So how many ways can I go from, say, city 2 to 1 on a red airline? 2 to 1, that is row 2, column 1. There are 2 ways to go from 2 to 1 on a red airline. 2 of them. Great. How many ways can I go from 1 to 1 on the blue airline? That is city 1 to city 1. There it is. 2 ways to do that. So that means there's a total of 2 times 2. There's 4 ways to go from city 2 to city 1, stopping at city 1 on a red first and a blue second. If you get lost, look at the diagram. There are 2 ways to go from city 2 to city 1. Yes, there are. There they are. And then there are 2 options which go from city 1 to city 1. Are there? Yes, 2 blue options to go from city 1 to city 1. So that makes for a total of 2 options times 2 options. Yes, I'm right. 4 options. All right, but notice we took this entry, multiplied by that entry, and got 4. Now we do the same thing again. To go from 2 to 2, that's to go from 2, row 2, column 2, there's 1 way. That's that entry. And then 2 to 1 in blue, row 2, column 1 is this entry. 1 way. That must be just 1 times 1, 1 option to go from city 2 to city 2 to city 1, red and blue. City 2 to city 2, yep, 1 way, that's it. City 2 to city 1 in blue, 1 way. There's only 1 way to get from 2 to 1 with a layover in 2. Great, but again, now I've gone now I'm sort of following this row, I'm kind of following this column, but I've now multiplied together the second entries. 1 times 1 is 1. Final route. 2 to 3 in red. City 2 to city 3 in red, there's 2 ways, it's that 2 there. 3 to 1 in blue, so that's row 3, column 1. 3 to 1 in blue is that 1 there. Must be a total of 2 times 1, which is 2 ways to go from city 2 to city 1, red, blue, with a layover in 3. And I think I'm right. 2 to 3, 2 ways in red, 2 choices, yep. 3 to 1, 1 way in blue, yes. Total of 2 options. But again, I kind of work my way along this row, work my way along that column, and multiply the third entries this time. 2 times 1 is 2. And then the total number of options I have is 4 options plus 1 option plus 2 options. I'm going to add them up. It gives me 7 options in total. 7 options in total. So to actually do a combined route, I actually start doing a new matrix, which is going to be a table of all the combined ways I can do it. To go from 2 to 1, row 2, column 1, I'm getting 7. Getting 7. But here's the thing, here's the thing. To get the total number of routes from city I to city J, with some layover in between, first going red, first going blue, just choose the ith row of A, the jth column of B and just multiply the entries in turn and add them up. That is called matrix multiplication. For example, if I want, say, first row, first column of this product matrix, just go first row, first column, 2 times 0, 0, plus 2 times 1, 2, plus 1 times 1, 2, there must be a 3. To do, say, first row, second column, just do literally first row of matrix A, second column of matrix B, and add them up in turn. 0 times 1 is 0, 2 times 0 is 0, 1 times 0 is 0, 0. Apparently, there are no ways, it's impossible for me to go from city 1 to city 2 by first going red and then going blue. Check that. Apparently there's no way for me to go from city 1 to city 2, first going red and then going blue. If I go this red, then I can't do a blue. It will take me away from city 2. If I do, what other red do I have? I can do this red, then there's no blue that takes me to city 2. I can't go from city 1 to city 2 by first doing red, then blue. It's right. Beautiful. And I can go on and fill out the entire matrix. We call this new matrix the product of A and B, and its name is going to be, believe it or not, A times B. People sometimes write A times B with an X like you do in algebra or arithmetic, or actually what you do in algebra is just write the two letters next to each other. That's the product matrix AB. To work out the entry on, say, the third row and the fourth column, just multiply the third row of A by the fourth column of B, and bingo. Multiply individual entries, add them up, off you go. All right, so that means the matrices need to have special size. That is, when you do a row of A, the number of entries in any row of A must match the number of entries in any column of B. You can't have a mismatch. Now, they don't have to be square matrices. You can still probably do some matrix products if you've got the right number of columns and rows, but sometimes the matrix product won't work out. So let me clean the board and give an example of what can go right and what can go wrong. Back in a moment. Okay, here are two matrices, M and N. M is 2 by 3, and N is 3 by 1. 3 rows, 1 column. So, can I work out the matrix product M times N? Well, let's see. There would be 5, negative 1, 10, 7, 4, negative 2, times 1, 2, 3. Okay. These are rectangular, definitely not square. The question is there good matching up of the number of rows and columns that I need to actually do this product? So to do a product, I need to take a row of the first matrix and multiply by a column of the second matrix and make sure I'm adding each entries in turn and there's enough of them of each to make it work. And the answer is yes. 5 times 1. Negative 1 times 2, 3 times 10. That's 30, take away 2, 28, 33. I believe the first entry is 33 for row 1, column 1. And then row 2, column 1, 7 plus 8 is 15, take away 6 is 9. 9, and that's all I can do. Therefore, the product of M times N must be this little matrix that's just 2 rows and 1 column, 33, 9, if I did my arithmetic correctly. Did I do correct arithmetic? I often make mistakes. All right, so M times N makes sense. Then, I bet if I tried the other way around, N times M, N times M, that would be this matrix 1, 2, 3, times this matrix 5, negative 1, 10, 7, 4, negative 2, row and a column. So we're going to do row 1, which is just 1 entry, and column, 1 entry here for this row, and 2 entries there, 1 and 5, and there's nothing to go with the 7. There's a mismatch. There's a mismatch. So you've got to make sure things match up nicely, then you can do a matrix product. If things are always square matrices, so you've got 2 square matrices of the same size, then everything is fine, because you know everything's going to match up exactly, because everything's identical in count. But when you get to the truly rectangular matrices, you have to be careful when you can do the products and when you can't. All right, so well, let me give you a little practice problem, and then we'll carry on. Okay, matrix P has entries x, 6, 4, 3. It's a 2 by 2 matrix. Matrix Q has entries 2, 3, 2, 1. Please find me a value x so that when you work out the product P times Q and you work out the product Q times P, you actually get identical answers. What value of x makes that work? Try it out. So these rectangular arrays of numbers called matrices do have an arithmetic. We've already shown how to double matrices and triple matrices, scalar multiplication. We've shown how to add matrices. We've shown how to actually subtract matrices, just multiply by -1 and then add. And we've also shown how to multiply matrices. In fact, there really is an arithmetic going on for matrices. So actually, there's something special going on with a particular type of square matrix. For example, people like to give a matrix which I'll call I, people call it the identity matrix. It's a square matrix that has nothing but ones along the diagonal and 0 everywhere else. I'll do a 3 by 3 square matrix. That's the identity matrix. Or the 2 by 2 version would be, ones on the diagonal and zeros everywhere. Ones on the sort of the southeast diagonal. All right, so the nice thing about this identity matrix is that it has a lovely property for matrix multiplication. If I take the identity matrix and I take any other matrix, in fact I'll be literally any other matrix, so just write down the 9 numbers, so if it's 3 by 3 here, or choose a 3 by 3 here, check, you should actually check this, show that the identity matrix times A, it just gives you A again. And the other way around, A times the identity matrix gives you A again. That is, this number doesn't change the matrix upon multiplication. Just like in ordinary arithmetic, the number 1 doesn't change numbers when you multiply by 1. The number 1 keeps numbers the same under multiplication. This identity matrix keeps matrices the same under multiplication. And just to cover ourselves, we'll stay with the square matrices, so all the rows and columns match up. Pretty amazing. Try it out. Double check for yourself. This matrix really keeps things unchanged under multiplication. Do it. All right, so our arithmetic of matrices is growing and growing. We know how to multiply matrices. We've got some matrix that acts like the number 1 under multiplication. The identity matrix keeps matrices unchanged, which now makes you think, okay, in ordinary arithmetic under multiplication, every non-zero number m, which is ordinary arithmetic, has matched with it its reciprocal, which has the property that m times 1/mth, non-zero, gives me back to the number 1. Which makes me now wonder, is the same thing happening with matrices? If I give you a matrix M, big M, remember matrices are usually denoted with capital letters, I'm wondering if there's another matrix, which I'll call its reciprocal, but people tend not to write 1 over a matrix. It looks a bit weird to people, so they tend to use this notation, M minus 1, that gets me back to being the identity matrix. Does that happen? Now, in ordinary arithmetic, we know the number m has a restriction, it can't be 0, so I bet matrices have some kind of restriction too about when its inverse exists. So, I wonder what that is. So let me give you a couple of puzzles to explore when a matrix inverse might or might not exist, and then let me come back and talk about it a bit more. So here comes my first puzzle. All right, let R be the 2 by 2 matrix 1, K, 0, 1. K is just some real number. S be the 2 by 2 matrix 1, negative K, 0, 1. Then I claim that R times S, when you multiply it out, gives you the identity matrix. And the other way around, S times R, when you multiply that out, also gives you the identity matrix. So I'd like you to actually verify that, please. Because that would then mean these two matrices kind of undo each other. They bring us back to the identity. That means they're matrix inverses. So check it out. Am I right? Okay, consider this 3 by 3 matrix Q, 0, 0, 0, 15, 3, 7, negative 2, 8, 4. Explain to me why there can be no 3 by 3 matrix M such that Q times M equals the identity. We have no hope of finding an inverse matrix to Q. It's not invertible. Why? Why can I say that? Figure it out. Okay, it turns out there's a very robust and complete theory about when inverses exist for 2 by 2 matrices. For example, if I give you just a general 2 by 2 matrix, A, B, C, D, then what you can do is the following. Turns out m minus 1, the inverse of m, exists and will actually equal this matrix here. That is, you've got the same numbers A and D on the diagonal but switched around, and you've got B and C on the other diagonal but now made negative. But then there's a factor of 1 over this number, A times D, take away B times C. Crazy. I know this seems crazy, absolutely crazy. That turns out if you do that matrix, provided this number is not 0, otherwise I can't do the fraction, so I need that to be not 0. If it's not 0, I can actually make that fraction, then just reorder the entries this way, then this new matrix actually is the inverse of m. That is, m times m minus 1, that matrix times that matrix gives me the identity, and other way around, this matrix times that matrix also gives me the identity. Whoa, complicated. Well, the practice question is verify that. Actually multiply that by that and see what I'm saying is true, and multiply that by that and verify it again is true with the identity. So that gives a complete theory about when inverses exist, and many, many curricula want you to just have this in your head. Don't know why, but they do. All right, in which case, I guess one has to have it in one's head. In fact, this comes up a lot. This is the key thing, that quantity, A times D minus B times C, is given a special name in matrix theory. It's called the determinant of the matrix. The determinant, in some sense, it determines whether the inverse exists or not, at least in the 2 by 2 case. And people often give it the notation like an absolute value of m, some sort of measure of the size of m. In fact, I will talk about determinants later on in another video. It has a nice geometric meaning. Other books might call it the det of m for, well, determinant of m. All right, so unfortunately, this is kind of unbeautiful and unnice and not much thinking here, but there is the formula for the inverse of a 2 by 2 matrix, provided the determinant is not 0. All is good to go in that case. All right, so I guess the right thing to do is, well, I've made the board messy, but please verify what was on the board earlier on. Okay, here's a little practice question. If A is x minus 1, x, 2, and 2x, and the determinant of A is 336, what would x have to be? Okay, just to end off, here's something fun. Look at the 2 by 2 matrix I'll call F. That's 1, 1, 1, 2. Work out F times F, F squared. Work out F times F times F, F cubed, F to the 4th, F to the 5th, and so on. And I'll bet you'll see the Fibonacci numbers. This matrix actually generates the Fibonacci sequence. Play with it and see what I mean by that. Give it a try.